Recorded is completed. Okay, so the recording was started. Okay, can we put it in this full screen? Yeah. There you go.
It's okay. Right. You can stand around here so you're visible.
Okay. You're fine. Yeah, that's fine.
All right. So the next speaker is Yenting Lin, and we're going to be hearing about knowledge-grounded conversational data augmentation. So you have the floor.
Hello, everyone. I'm Yenting Lin, and I'm glad to be here to talk about my research on knowledge-grounded conversational data augmentation with generative conversational networks. And this work is done during my internship with Amazon Alexa AI and in collaboration with Alex, Xiuquan, and Delay. So I'll first give an overview of the task and introduce generative conversational networks. And next, I will show the result of applying this method to open domain and knowledge-grounded conversations. Finally, I will conclude some thoughts on the results. Our motivation for this work is to improve the state of the art in conversational AI by addressing the lack of large and rich conversational data. Collecting high-quality conversational data is laborious and expensive, and remains a major challenge for further progress in this area. While research efforts are going to collect such data, but there are still challenges, including scalability, privacy, and data qualities. In this work, we focus the task of response generation under two contexts. The first one is open domain, and the last one is knowledge-grounded conversation. So for open domain tests, the conversational agent are given a context consisting of a list of previous utterance. Here we represent it as C, and consists of utterance 1, utterance 2, represent the utterance from both user or system sides. And our goal is to generate the most appropriate response U_n for the given context. To formulate knowledge-grounded conversational agent need two steps: knowledge selection and response generation. The conversational agent should therefore first select relevant knowledge pieces from the current dialogue context, and then generate a response that incorporates the selected knowledge. So in our setting, our conversational agent is also given a context C, and then we will use a TF-IDF retriever to find the best matching knowledge pieces for the given prompts. And we conducted pilot experiment comparing TF-IDF, BN25, and dense retriever. And we saw that the more sophisticated retriever did not outperform TF-IDF. So that's why we are using the TF-IDF retriever here. So finally, we're generating the response based on the retrieved knowledge pieces and the context. Our work is based on a previous method, GCN, Generative Conversational Networks, so which is a meta-learning approach that can be used to generate label, diverse, and targeted data. In our previous work, we showed that the GCN can be used to generate data for intent detection tests and slot filling tests. So in this work, we aim to show that GCN can also apply to generate data for response generation tasks. So to give a higher level overview, GCN is composed of two models, a data generator and a learner. The generator produces new data, which is then to train the learner. The quality of the generated data is used as a signal reward to train the generator, so that over time the quality of the generated data increase. So this reward signal can be used to guide the data generation towards desired properties in knowledge-grounded or open domain dialogues. So here's an overview of our method, and let's start with the seed training data. To study the effectiveness of our approach in low resource setting, we randomly select 10% of the original data for open domain and 10% of the original data for the knowledge-grounded conversation. And then we introduce a data generator, and we use a dialog GPT small configuration as initial model for the generator. So at the beginning of the training, we sampled the seed data from the original data set and then fine-tune the generator on these sample CD data. The input to the generator for open domain is just the dialog context. And for knowledge-grounded conversation, the input is dialog context plus the selected knowledge pieces. So the both target output are the next response. So in the first phase of the process, the generator is given some dialog context sample from the seed training data. And in knowledge-grounded conversation, we also give the retrieval knowledge pieces from the retrievers. So specifically, we give the last two terms as context and top three matching pieces as a knowledge and as a generator to predict the next system utterance. And we use nuclear sampling to produce multiple system response under the same context, so that the generator could be more diverse. And in essence, to create the augmented data set, instead of taking the human response from the data as a target, we use a generator response as our target and feed that along with the dialog context and knowledge pieces to fine-tune the learner. So at every iteration, we spawn a new learner from the pre-trained models, and we fine-tune it jointly on the augmented set and the seed training sets. So the learner is trained using a cross-entropy loss. The learner is then evaluating on a separate seed validation set to compute a numerical rewards. The reward is based on several metrics. For open domain, we use a combination of BLEU, Roach L, and BERT score. For knowledge grounded, we use the reward is BLEU plus knowledge F1. And for knowledge F1 measures the F1 score between the produced response and the ground truth knowledge pieces. So intuitively, it measures the overlap between the knowledge and the response. And then for updating the generated that produce the augmented data, we use proximal policy optimization, short for PPO, and with the following modification reward to train the generator using the learner's validation performance. So the first term here, small RCU, is a generation matrix that I mentioned in the previous slide, BLEU, Roach, BERT score, knowledge F1. And the second term is the KO divergence between KO divergent regularization term that prevents the generating from diverging too much from a reference and large language model. So the gref here is just a pre-trained dialog GPT. So after the GCN training is finished, we pick the best performing generator track point measured by the learner's performance on the validation set. And we create a final augmentation set that is usually much larger than the seed training sets. We then create a new learner as our final learner and fine-tune it jointly on seed data and the large augmented data sets. So if the augmented data is of good quality, we should expect the learner to outperform as it trained with more data. So the result present next are all computing on the final ones. So that is our method for training a data generator and produce a larger set of augmented example and for final learners training. So to evaluate GCN as a data augmentation method for conversation with and without knowledge, we conduct few-shot experiment on Topical Chat. And Topical Chat is a set of human-human conversation without explicitly defined roles for each participant, and is collected over Amazon Mechanical Turks. And each participant has access to a set of articles or facts, and in the chat, they will use these to have a conversation with another participant. So for open domain conversation, we sample 10% of the topical chat as seed and use dialogue GPT and BART as our initial model for data generator and learner respectively. In this experiment, we compare the learner performance we compare the performance of the GCN learner with 3 baseline. The first baseline is BART 10%, short for BART 10, which is a version of BART that is only trained on the same seed data. This is a direct comparison of the performance of the learner with GCN with augmentation, with augmented data or without data augmentation. So the second baseline is BART 100. So this is a baseline BART that trained with the full chat of the topical chat. So this is kind of upper bound on the performance of the learner. So as it is using much more large amount of human authored data. And the third baseline is GCM without reinforcement learning, GCM without RL, which is a version of BART that is trained on a C data set and a synthetic data set. But the synthetic data set is generated by a data generator without updating via reinforcement learning. So this is a comparison of the effectiveness of the GCN reinforcement learning approach against a baseline that is not using reinforcement learning at all. So in open domain condition, we see that BART 10 outperformed GCN agents on all automatic metrics. So that is on the left part of the table. So due to the intrinsic one-to-many problem of the conversation response generation, reference-based metric may not correlate well with the human ratings. So our generated conversation may be also appropriate for the dialogue context, but different from the reference corpus. So for this reason, we also conduct human evaluation. So that result is on the right part. So human evaluators will rate the output of the GCN learner, the baseline, and also actually the data, the ground truths. So specifically, they rate how engaging, how fluent, how relevant each response is on a scale from 1 to 5. So we generate 1,000 examples for each condition using the same context and make sure we have 3 ratings per example per condition. And we see that in the open domain condition, the GCN learner produce engaging but less relevant conversation. So this is likely because the model insert facts or other outputs that is not entirely relevant, but would be perceived as more engaging by the annotator. For example, information on a relevant subject or some fun facts would be inserted into our response. So overall, averaging the 3 metrics, GCN with reinforcement learning, which is a method we propose, outperform BART 10, and it's very close to BART 10 on the full shot data set in human evaluation. So let's move on to the main focus of this work, knowledge grounded conversation. So we sample 1, 5, 10% of the topical chat as seed, and we use dialogue GPT, also use dialogue GPT for a generator, and this time Blender bot for the learners. So in this experiment, we compare the performance of a learner with GCN against 2 baseline, Blender bot 10, which is very similar, a Blender bot trained on the same seed data, and a GCN without reinforcement learning. So it's trained on seed data and synthetic set, but the synthetic set is produced by a pre-trained language model. Without reinforcement learning updates. For automatic evaluation, we see that GCN with reinforcement learning is able to incorporate more knowledge as evidenced by higher knowledge F1, KF1 under all settings and under all settings. And additionally, the fluency of the generated dialogue is also comparable or even better than the baseline as suggested by the perplexities. So for human evaluation, we also study the performance of both data generator in the GCN and the final learners. So we see that the learner with GCN with reinforcement learning produce more engaging, fluent, relevant conversation, and overall outperform both baseline, while against being close to blended bar trend on 4 shot of the data. So in the pairwise comparison, what that is the lower part of the table, the GCN with reinforcement learning is generally preferred more than the other two methods. So we compare against the blender bot and with reinforcement learning and without reinforcement learning. So overall, for the GCN condition, we're given that we generate 5 times the seed data, the total amount of augmented data is actually only 6% of the size of the few shot topical chats. So our result will show that the generated data is indeed of high quality, since the same model using our generated data perform close to the one that's used the full shot of the human author data. We further analyze the performance of GCN, especially its performance with respect to the number of generated update iterations. So we see that perplexity decrease and the knowledge F1 increase as we have more iteration, meaning that the generator actually leads the learner to learn to produce more fluent and at the same time knowledgeable response. So, but blue score naturally drops as these more knowledge response may not appear in the human response, in the human reference corpus. We also analyze the performance of GCN with respect to the amount of generated data. We vary the amount of synthetically generated data as a multiplier of the size of the seed data. 1 means the number of generated example is equal to the amount of the seed data. 10 means the number of generated example is 10 times more the size of the seed data. So we see a similar trend with the increase of the GCN iteration, that perplexity dropped from 26 to 22, and knowledge F1 increased from 0.20 to 0.27. So this means that the generator is able to learn the distribution of the data from the seed example and generate more diverse, high quality example as the number of generated example increases. So here is an example in the open domain conversation. So the last row GCN with RL. So it said, did you know there are more than 30 million players in the NFL? Which aligns what I said, that our model will memorize some knowledge and insert some topics that is not actually have high overlap with humans response, but that is also engaging. But it's less, if you calculate automatic metrics, it will appear less relevant. So for example, in the knowledge grounded conversation, we found an interesting knowledge pieces in the third row of the retrieval knowledge. The highest paid state employee is either a college football or a basketball coach. And our model is able to incorporate the knowledge and produce fluent response that mentioning this information. So for conclusion, we represent a data augmentation that is based on GCN to generated data grounded on textual knowledge. And we show that given a small set of seed data, our approach can generate high quality data, and that could be used to train a competitive conversational agent. And human evaluation and analysis indicates our method generate diverse data, which is beneficial for task learning. For future world, our method can be further incorporated with more reward metrics, such as user satisfaction for open domain or task completion for task-oriented domain, to cover a wider range of conversational tasks. And by exploring more model architecture, we believe that could also improve the quality of the generated data. So this is our overall framework. Our paper link is here, so please check out for more details. So I'm happy to take questions now.
Thank you. So do we have any questions? Okay.
Have you analyzed why the TF-IDF-based retriever performs better in this pilot experiment than the more sophisticated one? And which kind of more sophisticated retriever did you use?
We use dense passage retriever without fine tuning on our target data set. So I think that is the main reason why our sophisticated retriever like DPR doesn't work out of the box for our data set. So actually in details we are using Topical Chat. So we tested on scene test sets, so that so we mentioned that in the paper. So usually the dialogue context is not really relevant to the knowledge pieces. So that's why by only mentioning some token levels, which are used by TF-IDF, it works reasonably well.
Okay, thank you.
There's one more question down here.
Hi, yeah, I like the work. I had a similar question, or I guess more general. I guess I don't really understand the purpose of the knowledge grounded conversation. And it's maybe, I mean, I know it's been done in previous work too, but one thing is your definition. I wasn't clear on whether that was a definition of the problem, the TF-IDF similarity in extracting the knowledge, or is that really part of the solution that you need to work on? I mean, it doesn't seem like it's easy to independently validate the two pieces of selecting the most relevant knowledge to the previous conversation versus producing an appropriate answer. And I guess with the evaluation, is it when you're evaluating how much knowledge is coming out, is that going utterance by utterance, comparing each utterance to the knowledge that was selected for that utterance, or is it saying that somewhere in the dialogue, not necessarily this utterance, but you're going to reveal the knowledge that you found so far? Sorry, that's a lot of questions.
Yeah, so our human evaluation is conducted in alternate space. So for the same context, we produce a response for baseline of our learners using the same context. So that is on the alternate space. So if your question is where, I think my answer would be that we want to incorporate knowledge into every alternate, every turns in the dialogues. So, and we do this in turn-based. So, yeah. So we're not considering it.
Intuitively, as you're progressing through a dialogue, a lot of the context is the same. You just keep adding on. And so some of the knowledge retrieved you would expect to occur multiple times. So are you going to get a better score if you repeat what you said in the previous utterance?
We didn't investigate that, but that is a really good point. As the dialogue progressed, the agent might have more ways to use the knowledge mentioned earlier. But yeah, I think it will be interesting if we investigated further into turns in the later part of the conversation.
Do we have one last quick question? Okay, if not, then thanks again for your talk. We can move on to the last speaker in this session.